And when we do have an arrhythmia that could be could be caused by ischemic changes. Now, when this arrhythmia happens, that's another important factor. Mostly the ischemic heart disease associated arrhythmia usually is happening when you do some kind of exercise, some kind of effort, when the heart rate increases. A lot of you, especially during the exam period, I think sense that you had several premature beat formation, but this happening at rest. And if you start moving, when you wake up and you move around, this kind of arrhythmia disappears. So that's, let's say, this due to the anxiety, the increased stress situation. Now, if we continue to obliterate, let's say, the vessels, the ischemia transferred to a more severe condition that is called angina. Now, of course, there are several types of angina: the silent angina, the effort angina, the unstable angina, the principal angina. This is what you can read before that I point you out which videos you should watch, or during the lecture, Tornolzi already mentioned about this type of angina. So the angina is a very typical pain that the patient says. In this situation, however, especially when we are talking about the stable angina, the lumen of the coronary is already obliterated more than 70% if we have a stable angina. So this is not an early phase of detection that we could have. And another type of angina is the unstable angina, that usually the pathomechanism is different from a stable one, because that's a vulnerable plaque rupturing up and the small vessel is occluded. However, when we do have the coagulation starting, the fibrinolytic cascade already be active and dissolving the small plaque. This is why the patient won't suffer of any kind of final closure. If you think a little bit, this heart muscle, heart cells can survive about 1 hour in an ischemic milieu, not more than only 1 hour. And if you cannot reperfuse this area within 1 hour, relatively the necrosis, the dead tissue formation occurs. And this is when we're talking about MI, myocardial infarction. Now, in an unstable angina, the matter of the chance that the size of the plaque that is liberated from this vulnerable plaque and closing a small or a bigger artery. So this usually, if somebody has this kind of angina, unstable angina, it should be taken to the CVC and should be evaluated very carefully. This is why it's a part of acute coronary syndrome. Now, if we do not do anything, relatively, we develop a more severe condition when disclosure occurs, when a bigger artery is clogged, and without interfering this situation, the patient will develop necrosis. However, today, if we can, let's say, figure out or diagnose early this kind of situation, the patient taken to the CVC and they implant a stent and reperfuse this area, and necrosis won't develop. So this is how it changed today's, this kind of MI, what we're talking about, the MI, because that's a hyperacute MI, but if you solve the problem, the patient never had, let's see, necrosis. Now, let's see, first of all, what kind of sign of ischemia can be seen on ECG. Now, on ECG, not every type of ischemia can be seen, and neither the MI. About 50% of the cases, you can see some changes on ECG only. Now, let's see the ischemia. Normally, if you know that, normally the depolarization goes from endocardium toward the epicardium. However, the vessels, the coronaries, goes from the epicardium to the endocardium. This is how they perfuse. And of course, you do have some collateral circulation between the coronaries. However, this collateral circulation is not enough if you do have a closure, so relatively this small connection, we cannot supply the closed area. in certain other animals, for example, the dogs and other, this collaterals is much bigger one. There's a chance, if you do have this obliteration taking place very slowly, there's a chance that collateral circulation will develop and the patient can survive and they do have a complete closure, but don't count on it because in your case, it won't happen. Now, let's see the depolarization. The depolarization goes from endocardium to the epicardium, and this is why if you place an electrode over the heart, you detect a positive deflection because it's depolarization vector pointing toward the outside area. Now, you know that physiologically, the repolarization will start whenever the depolarization ended, so in the epicardium. So it's going from the epicardium toward the endocardium. This is why, because this area, the epicardium, had the, let's see, the least time, a very few milliseconds it had before deposition starting. And this is why it's depending, the deposition depending on the amount of ATP that can be used to pump out the sodium. So it's a little bit starting slower, but it's speeding up because this endocardial area, they already had enough time to produce enough ATP. So if you look at the, let's see, the shape of the T wave, it's never symmetric. First is a slope is, let's see, is less, and after finishing faster. So this is why this kind of T wave is not symmetric. This is what you can look at it. Now, what will happen in the mildest condition when we do have a problem with the endocardial, the subendocardial area? This has the reverse circulation. So what will happen? Relatively, the depolarization is not altered, not at all. The repolarization at the beginning is not altered. However, in the later phase, because this area is ischemic, so relatively we do have an anaerobic condition that can generate ATP, and that anaerobic condition does not have that efficacy than the aerobic condition. This is why the last part of the T wave a little bit flattened, and this makes the T wave symmetric one. Now, so in this case, when we do have a subendocardial ischemia, the T wave be symmetric, maybe a little bit taller. The T wave that is symmetric, it looks like as a triangle. Now, and of course, the patient possibly doesn't have any kind of clinical symptoms in this situation. What will happen when we do have a subepicardium involvement as well, or the transmural, doesn't matter, it looks like a transmural. So when the all, let's see, cardiac muscle is affected, the depolarization doesn't need energy. Okay, the sodium can flow in freely. However, as you see here, the repolarization cannot start it from the epicardium because this is where the depolarization ended first. So the most time what we had is in the endocardium. This is why we have more ATP synthesized by the anaerobic condition in the endocardium than in epicardium. It had much more time. So this is why the repolarization is changed and is starting from the endocardium and going toward the epicardium. This is very, very similar when we had a ventricle, for example, premature bit formation or a ventricle bit, that again, the repolarization and the repolarization has the same kind of direction, but because they are moving different charges, this is why it's exactly the opposite, inverted. So the T be inverted, and this is what we call as a coronary T. Between that we do have a coronary T, negative T, or flattening or biphasic, anything can be the sign of ischemia. Now, if we go on and when we do have a more severe closure, such as in the stable angina, as mentioned, more than 70% of the lumen is occluded, now the lesion occurs. Lesion means that the cells cannot maintain the normal membrane potential. As you see here, this is a normal cells. Here, the cells that cannot, let's see, has as negative intracellular negativity as a normal one. So what it means, still some sodium, for example, stays in, and this is why the basic membrane potential, the resting membrane potential, a little bit more positive comparing to the normal area. So it's meaning that on the surface, we have more negative charges. So at rest, we do have a bipole, a resting bipole, or that's a, let's see, this is injury current that is pointing always toward the normal area. Now, and then another thing, if you're looking at the charges, as you see here, in a normal area, normal cells, you do have much more positive charges. So the gradient that pointing intracellularly is higher comparing to the area in the lesion. So this is why not only the diastolic current that we do have, but we do have a systolic injury current as well. And because relatively less positivity can flow in the lesion than in a normal situation. So this all will influence the shape of the QRS complexes. And depending on which part of the ECG is altered, that we do have, let's see, the systolic current and the diastolic current. This is one, the systolic current influences the ST segment, while the diastolic current will influence the PQ, and the QT segment usually is suppressing this segment. Now let's see what will happen. In the lightest ischemia or lesion, when we do have a subendocardial lesion, as you see here, this area is relatively more negative comparing to the healthy area. So what it means? It meaning that this diastolic current is relatively pushing up the baseline. So we always have a little bit more positivity in the surface area. So the baseline is shifted up. On the ECG, when we are recording the ECG, you do not see the voltage. You see only the changes. We have no idea what the 0 millivolt is. We only see that the ECG somehow is changing, and we say that, okay, this is 1 millivolt changes. But usually you set, let's see, the pen in the middle of this area, but you have no idea what kind of potential difference we do have at rest. Now, in this situation, we do have a little bit more positive baseline. So what will happen when we do have a depolarization? Everything starts from here. And when you discharge the whole area, including the normal and the lesion as well, there is no potential difference can be detected outside. What it means that you are going back to the absolute 0 millivolt baseline. And when you're finishing the depolarization. And what will happen when the repolarization occurs? When the repolarization occurs, yep, we are restoring the false baseline. And what we have here, as you see here, the ST depression. If we do have this ST depression. Now, the ST depression, we are assuming that ST depression is pathological if in the limb lead, so 1, 2, 3, AVF, AVR, AVL, this ST depression that we're comparing to the PQ interval, that it's more than 1 millivolt or half millivolt. Let's see, half millivolt, not 1 millivolt, but half millivolt. So half millimeters. And if we do have, let's see, an other condition in the chest leads, let's see, in the chest leads, you have 1 millimeter done. That's already a pathological ST depression. And what kind of clinical symptoms can be seen in a subendocardial lesion? Stable angina. Now that can mimic the angina. So that's be a pain. Okay. Now, if we do have a subepicardial, this kind of mass is not located in the right place. It should be here. So as you see here, the lesion that is located in the subepicardial area. Now we do have a bipole that pointing toward the endocardium. So the baseline is shifted down. If the baseline shifted down, the depolarization starts here, okay? And when you discharge, you are going to the absolute 0 millivolt area, and the repolarization restore the baseline, the fast baseline. So as you see here, we do have the ST elevation. Now, ST elevation is pathological if you do have more than 1 millimeters above the baseline in limb leads and 2 millimeters above the baseline of the chest leads. Okay, this is what it meant. Usually, we looking at the J point, that the J point is usually behind the S point, about 0.8 second behind the S wave. So this can be the J point that you are, this is a J point, for example, starting right here. As you see here, a little bit, the curve is changing. Now, if you do not restore the circulation, and in unstable angina, it needs about almost an hour, almost like, let's see, almost 1 hour that is needed, but it's still restoring the normal circulation. However, if you do have a bigger clot, you cannot. And if it's more than 1 hour, what will happen? The tissue will necrotize. A necrotic tissue necrotic tissue doesn't have any electric activity. What does it mean? There is no depolarization, no repolarization. So if you're assuming that if you cut the, let's see, the chamber of the ventricle, that's about symmetric. And when they're starting the depolarization starts from the endocardium toward the epicardium. Whenever you do have the necrotized tissue, there is no electric activity. And this is why in this point, what will happen? Everything goes away. So the vector goes away from this area. This is why they call it a window. It looks like you're looking inside the heart. And electrically, you do detect a negative Q wave. The first wave is a negative, first negative wave, the Q wave, a pathologic Q wave where the necrosis occurred. Of course, in the opposite wall, you do see the opposite because that's a mirror image. You will see a taller R wave. Now, not only the Q can be the sign of the necrosis, but, for example, R reduction can be as well. Well, it's not exactly true, but the subendocardial necrosis, of course, less tissue, less electrical activity. So this is why the R wave be smaller in those areas. But this R reduction can be seen very nicely if you are looking at the V1, V2, V3, V4, because normally the transitional point is between V3 and V4. Now, if you do not have any enlargement of the initial R in V2 and V3, you can assume that is R reduction and can be the sign of a necrosis in the anterior lead. Now, what is the pathological Q wave? Because that will represent the necrotic tissue. Now, in those leads where we should see normally Q wave, that Q in the pathologic Q is wider and deeper. Wider, it means at least 1 millimeter. And the size or the depth of the Q is at least 1/4 of the R wave. Now, if it's so, fine, you will see that that's a sign of necrosis. And an additional one, this Q wave has these Q waves because it should be seen at least in 2 leads, 2 consecutive leads. So if you do see in, for example, 2 AVF, it's okay, or 3 AVF, yes, that's a necrosis. But if you do see it's only 3 without seeing in AVF or 2, that's not pathological Q wave, okay? Or in V1, V2, if you do see, yes, that's pathological one. But if you do see only in V1, is not pathological one. So when we diagnose ischemic changes, it should be seen in 2 consecutive leads. Now, if the Q wave is seen as lead V1, V2, V3, any kind of small wave, because we should see initial R wave in V1 to V4. And an additional, let's see, definition of this pathological Q wave, if you do have a recording of the patient previously you recorded, and that never had any Q or the Q wasn't as deep as right now, you can assume that that could be a necrosis. Okay, well, all right. So how to diagnose acute myocardial infarction or STEMI or non-STEMI? Okay, that's the difference between STEMI and non-STEMI. What's the difference one? If you do see the typical sign as an ST elevation on ECG, that's a STEMI. If you don't see any changes, but the necrotic enzyme, the cardiac markers elevated, showing that some kind of cardiac damage occurs, then that's a STEMI, what we call it. This is how you diagnose MI. This is why it's important to know about the cardiac markers as well. Usually when the patient has an attack, calling the ambulance, and ambulance taking some blood samples, but if the ECG shows something, okay, you don't need the blood samples, only you are proving that yes, the patient had some kind of cardiovascular problem, and the patient taken to the CVC immediately, fine. After they catheterize the patient, they use an angiography, they will see where the clot occurs, and after they're removing this kind of clot and putting a stent in immediately to the patient. However, if there is no sign on ECG, first of all, they are taking samples, okay, fine. If the markers, for example, the troponin T and I or a CK-MB isoform is not in the pathological range, after they will repeat about half an hour later or 1 hour later. And if, let's see, the values are increases, you're assuming that the patient has an end-stage myocardial infarction. Okay, good. Okay, yep. All right, now the staging is another important one. Now, what have we already seen that what kind of sign we can detect in a normal area? Yeah, we do have a QRS complex and a positive T wave. And when we do toward the ischemic area, as you see here for the positivity is changing, flattening the T and be negative, more negative, and the coronary T's occurs. And when we do have the injury, as you see here, the ST segment starts to elevate. And in MI, we do have a Q wave and ST elevation and T inversion. So that's in an echo. This is how the developmental occurs. If you close a vessel, and immediately after, ischemia will develop, injury will develop, and MI will develop. Now, this is the acute phase when the necrotic sign develops. Now, what will happen in a clinical feature? When the onset of the pain occurs, relatively, you almost don't see anything, but gradually, the T wave and the ST segment will be elevated. It looks like you're pulling up the ST segment. And in a hyperacute stage, that is usually within minutes, it doesn't take too much, maybe 15 minutes or so, or half an hour. We do have this dome-shaped ST elevation, and we do have a T inside this ST elevation. And of course, that can be the local hyperkalemia that occurring when you are blasting the cells. And this is ST elevation, fine. Now, we are assuming that this is a hyperacute stage of MI, that without any kind of intervention, the patient will develop necrosis. This is why these patients should be taken to the hospital. And within 1 hour, should be reperfused. And if you could reperfuse this area within 1 hour, there is no necrotic tissue will develop. So the ST segment goes back to the normal baseline, and the patient never had necrosis. However, if the patient taken to the CVC, maybe later on, maybe after 2 or 3 hours or so, well, necrosis will develop. And because this area, this lesion, cannot be maintained forever. That's like the clinical death for the cells. That's for a while. It can live on. However, some cells will die. These cells necrotized. Some cells, the circulation improving, and through ischemia, will heal later on. So this is why when we do have the acute stage, we do have all features. First, we do have the Q and ST segment. Later on, after several hours or days, we do have the negative T wave, the T wave be inverted, and that's be negative. Usually this happening in the late phase of acute. And later on, I said that there's no way that ST segment stays forever. This is why the ST goes back, and after maybe a week or so, ST segment goes back normally, Q wave stays, and some areas still ischemic one. So what we do have, a Q and a T inversion. There is a situation that can have a persistent ST elevation, but usually it meaning that the patient develop an aneurysm, and the heart in cardiac aneurysm is developed, and that always maintaining some kind of ST elevation. So that could be the clinical sign of an aneurysm. Of course, aneurysm can be ruptured anytime, so the patient had to be operated and removing the aneurysm. Now, in a subacute stage that lasts for month, for example, that only has Q and T inversion, no ST changes. The definitive or an old infarct, it's meaning that necrosis is always there. ST segment is not elevated, okay? The T wave, maybe the ischemic changes, maybe a circulation is improving a little bit. So it can be anything, can be flat T wave, can be normal T wave, anything can happen. But one thing is very characteristic one, that the pathological Q wave stays there forever. Now, why is it important to localize the MI, localize the closure? Because we want to know that which coronary is occluded. Of course, it's helping to the CVC to figure out the catheterization and where the plug is located and where the plug that should be removed. Okay, first of all, we do see the placed electrodes. For example, here it's placing the electrode V1, V2, V3, V4, V5, and this area is the anterior area. So as you see here, anterior, for example, V1, V2, V3, V4, that's an anterior one. Out of this one, the septal one, usually in V1, V2. Okay, now the lateral, V5, V6, high lateral, 1 AVL, whenever which area is affected. Mostly the same coronary supplies this anterior lateral area. This is why the anterior lateral very frequently develops, and that is called or anterolateral or called extensive anterior myocardial infarction. An additional one, the inferior 2, 3, and AVM, that's an inferior wall. Now the inferior wall, as you see here, the inferior area is usually supplied by the right circumflex artery that supplies the posterior area as well. This is why the infero-posterior MI is very common one. Very commonly they comes together because we do not have any posterior leads normally. What we do see in anterior lead, we do see the opposite changes. So we don't see ST elevation, we will see an ST depression. We don't see Q wave. Instead of the Q, we do have an R, prominent R wave. So exactly the opposite. This is what is called the mirror image. Or you can place an electrode on the back, for example, VD1, VD2, VD3, paradorsally or paravertebrally, you can place this electrode, or the continuation of the chest lead, you can place at V7, V8, and V9. And if you do see the sign of ST elevation also, as you can see, sometimes in V5, V6, you do see a little elevation when you do have an inferior MI, and that can be because a little bit this area of the inferior wall, or not the inferior, posterior wall, it's a little bit giving some signal on this V6, for example. Now, an addition cardiac marker, I don't want to talk, you should read it and you should know about the cardiac marker. One thing, and I want to say about the right ventricle MI. Now, why is it important, the right ventricle MI? Because mostly is associated with an inferior MI. And what you do see in this situation, that you do see a higher ST elevation in lead number 3 than in AVF, and sometimes they're putting the chest leads on the right side. So V3, V4 is placed on the right side, and you do see this ST elevation also. Now, why is it important to figure out a right ventricle myocardial MI? Because you should not give nitrite or nitrate to this patient, because that will cause a dropping of the blood pressure, and you can kill the patient. This is why it's important to diagnose a right ventricle MI as well. Okay, now this is what I wanted to say, or wanted to summarize it, and now we should practice. But before we practice, let's see, do you have any kind of question? R is fine, so it's meaning that there is no AV conduction abnormality. Fine, okay. So by summarizing so far, the rhythmic one, rhythmic heartbeats, okay, 60 beats per minute, sinus rhythm, PR is normal. Next one is the QRS is wide or not, because we proved that the impulse originated from the SC, went through the atrium, went down to the ventricle. Now, inside the ventricle, if we do have conduction abnormalities, the QRS should be wide. If not, there is no intraventricular conduction abnormality. Yeah, the QRS is narrow. Yes, this is what we go. Okay, the next one here, I like the axis, because now we are working on the QRS complex. Of course, when we studied, first we studied the axis because that was a basic one and you already heard about in physiology. But here, now we can talk about the axis. As you said, that 1 positive, AVF negative, 2 equiphasic, so it's a minus 30. You can assume that this is around, it's a left axis deviation, or because that's a more positive lead number 2 than negative, so it's a left axis deviation. Good. Next one, still inside the QRS complex, there is 2 things can happen. 1, pathological Q wave. Let's look through, do we have any pathological Q wave? Okay, this is one thing that you have to do. And after, whether the R's are too tall, let's look for the ventricular hypertrophies. Okay, now let's see the Q wave, because we haven't studied yet the hypertrophies. No. Okay, this is an initial R in V1, that's V1. AVR, yes, we do have Q wave, but only one lead, okay? AVR, no more, and AVR looking inside. Let's see the heart, so it's not. AVL, well, AVL, if we do see a small Q wave, but this is not 1/4 of the R wave, and I don't think that's a pathological one. Plus, I don't see any pathological Q wave in lead number 1, because what we said 2 consecutive lead, we should see the pathological Q wave. AVL and lead number 1, that's a high lateral lead. Okay, look at the chest leads. V1, initial R, we do see an initial R. Maybe I can get a little bit closer to show you that initial R. See, can you see the initial R here? That's initial R, okay? And in V2, yeah, we do see that very nice R wave, so the R progression, oh, I'm sorry. So we do see, yeah, it's initial R, okay, Q, R, R. So again, there is no 2 consecutive lead to see this Q wave. Maybe in V2 you do see this Q wave, but not in V1 or V3. So this is not pathological Q wave at all. Now you can talk about the ST segment. It's up to you now.
So I think that the baseline is a little bit pushed up. And
where?
In lead 2.
Lead 2. Why? That's a bit, it's meaning that ST depression, not lead 2.
Yeah,
Huh?
No, it's ST depression.
Okay, here, what you do see here, we do see this ST depression. See, that's ST depression. Yes, we do see the ST depression. Yes?
Yes.
Okay, okay. What else? What other area? 2, 3. Okay, go all the way. 2, 3, and AVF. For sure, we do see this ST depression because these are those leads that looking at, let's see, the diaphragm area. And what about here? What can you see in lead number 1? And of course in AVL. What do you see?
That's not a depression.
That is not a depression, that's an elevation. Now that's a pathological condition, ST elevation. This is what we are hunting for, the ST elevation, because that's the MI, the STEMI, okay? And you do see ST elevation in lead number 1 and AVL. Okay, now let's stick to this chest lead. Why do we have this ST depression in 2, 3, and AVF? Now, what do you think? Huh?
Because of the angina?
No. 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 Because lead number AVL is opposite lead number 3. Look at the XXL system. AVL is minus 30. Lead number 3 is 120. You should see the mirror image. If you do see a lateral ST elevation, you should see an inverted sign, a mirror image in the inferior lead. If you do have ST elevation in the inferior lead, you should see ST depression in the lateral leads, because those leads exactly opposite to each other. Okay?
Okay.
Now, plus you do see ST elevation in V1, V2, V3. Well, a little bit in V4 as well. Maybe in V5, V6, I do see this ST elevation. So we do see an extensive anterior MI, yes? Okay. So we do have an extensive anterior hyperacute anterolateral or extensive anterior MI, but hyperacute because there is no Q wave. Okay? Good?
Okay.
Okay. Let's move. Oops.
So
Let's
sorry,
move.
what's
Yes?
the answer of that slide? So
the slide is an anterolateral hyperacute STEMI.
Okay, thank you.
You're welcome. Okay, 102. Who has 102?
That was me.
Okay, now let's go step by step.
I would say it is regular rhythm.
Okay.
The heart rate is about 70 to 75 beats per minute.
A little bit less than 55. Okay, 1, 2, 3, 4 and a half. Okay, go on.
And then the impulse was, there's like a very weak P wave, I could see.
Okay, all right, now what we'll do if we don't see a very nice P wave, okay, P wave can be anywhere, especially here, you can see P wave here, okay, can you see this P wave here? Or in V1, you can see a P wave, or in lead number 2, you do see a P wave. Of course, this P is not so nice that it used to, but it's P and it's rhythmic and looks like every teeny tiny wave followed by a QRS complex. So you are assuming that that's a sinus P wave. Especially here, it's very flat, but it looks like a little bit negative P wave that we do have. Yes?
Yes.
Go on.
And then the shape of the P wave,
yes,
weak.
but yeah, we cannot say anything about the shape of the P wave, but it's very small. Now, when can be the P wave or the QRS complex small? A lot of cases, somebody is fat, very fat, that can decrease the electric potential differences. Or another thing that usually altering the size of the arteries and everything, if you do have a pericardial fluid. Another thing that can decrease the size of the R or the other ways. Okay, but let's assume that this guy is fat. Okay, it's okay. It can be that the P is smaller. Okay, go on.
Okay, and then the PR interval, it seems to be normal. And
PR interval normal. Okay, go on.
And the QRS is not wide.
Okay, very good. So the width of the QRS is okay. All right, axis.
The axis, because lead 1 and AVF are both positive, it's within the normal range.
Okay,
and
good.
Using the other leads, like lead 3 is negative and AVL is positive, so I would say it's between 0 to 30 degrees.
Okay, good.
And then
Pathological Q wave.
I don't think there's a pathological Q wave.
No, we don't see any. Okay, very good.
And then the R is tall, so it's good.
It's okay, that's normal. It's not normal, it's not taller than a normal. Okay, so it's no sign of hypertrophy. Okay, go on.
And then the ST segment. The ST segment was, I looked at the 6 leads, the 2, 3, 4, 5, 6. I could see the ST elevation.
Very good. And if you do see in V6, you should look at in lead number 1 and in AVL as well, because V5, V6 is a lateral lead, not a high lateral, but 1 and AVL is a high lateral. And I bet you that this is 1 millimeter. See, this, if you look at this is 1 millimeter. So that's again what we said before. That's an extensive anterior or anterolateral hyperacute MI. Okay. Good. I have to remove these annotations. Okay. Good, good. All right, good. Thank you. Now that was nice. That was nice, but I have to erase this too as well. Okay, 103. Who has 103?
It's mine.
Good.
It's rhythmic.
Okay.
And its heart rate is 90 BPM.
90. One. Yes, it's 90.
Great. When I'm looking at the P wave, it's normal.
Okay. Well. Well, yes. Okay, go on.
And the PR interval is also okay.
Okay, good.
And QRS is narrow. Yeah, except for lead 3.
Except in every lead, yeah, they are not narrow, because from the beginning of the QRS till the end, look at this. It's not normal. It's not normal. See?
Yeah, I mean, I can tell the Q is inverted.
Of course, every Q is inverted because Q is negative, so don't say this one. Okay, so it's meaning that the QRS is wide. That's it. Okay.
Okay, so this one is already QRS. Okay.
Okay, so what does it mean when the QRS is wide, but we do have sinus written? Okay. What does it mean?
What's it like? Hyperventricle? Is it something wrong with the ventricle signature?
Intraventricular conduction abnormality. Now, how can we figure out which bundle is blocked? We have to look at V1, and so that we have to look at the right ventricular leads, and we have to look at the left ventricle. Is that left ventricle? It can be V6 or lead number 1 and AVL. And whenever we do see the wide R complex, the block is there. Where do we have the wide R complex? Where?
Between V1 and V6.
But where? Where?
Oh.
Yeah, which lead has a wider R and bigger R?
V1 is.
Yes, so where is the block? So where is the block?
Right bundle.
Yes, that's a right bundle branch block. Yes, very good. See? Okay, go on.
Okay. And
so we do have a right bundle branch block. Good. Now what about the axis?
And the axis, it was hard to determine because I cannot tell whether it's positive or negative for lead 1 and...
Well, let's assume that this is a positive or equiphasic. Okay, this is equiphasic, fine. So it can be around 90 degrees, yes?
Yes, around 90 degrees. Okay.
Okay.
Can I say AVL is equiphasic? No?
Well, a little bit negative, I believe so, but in lead number 2 and 3 is positive, so and almost the same, so I would assume.
Oh, okay. Yeah, check the lead 2 and then 3. Oh, all right, I got it. All right, so that was the axis, negative 90.
Okay.
And we have pathological Q wave. Okay.
Now, where do we have this pathological Q wave?
I'm sorry?
Where do we have the pathological Q wave?
In V1.
And
V3.
And V2, and V3, and in V4, and in V5. So?
1, 2, 3, 4, 5. Yes.
Yeah, so we do have pathological Q wave. Fine.
Yes.
All right.
Okay.
And the same areas we do have as the elevation as well. So?
Oh, yeah, we have ST elevation. So it is, yeah, I wrote that one.
Okay, so?
I thought it's, no, not this one. I thought it's, never mind then. How can you tell it's ST elevation?
What should not mind? I have no idea. I'm not worried about anything, but okay, so let's summarize. We do have Q wave V1 to V5. It's meaning that's an anterolateral up to V5, anterolateral acute MI because we do have Q wave and ST elevation. Yes?
Q wave and ST elevation.
Yeah. Now, additional to this one, we do have a right bundled branch block as well.
Yes, that one I got. But how can you tell it's a ST elevation? I'm sorry.
How do you know that is ST elevation? Because you have to compare the ST segment, place of the ST segment based on the PQ distance. Yeah, see, it's ST elevation, not?
Oh.
Looks like as a sitting rabbit or a snake is swallowed an elephant. I don't know what you like.
Oh, I thought it was horizontal, but okay. Okay, thank you.
That's an ST elevation. That's the ST elevation. See, here, that's an ST elevation. Yes?
Yes, it is.
Okay. Usually everybody sees the ST elevation. They don't care about the Q wave. Now we have everything here. Okay. Good. All right, let's move on. Yes?
Could you tell me the answer of 103?
Now what shall we explain? Everything from the beginning.
No, just answer.
I got R bundle block.
Right bundle branch block, yes.
Yeah, right bundle H blocks, and I got anterior lateral acute MI.
Yeah, that's it. Nothing else.
Yes.
Thank you so much. You're welcome.
Pardon me? Somebody said something. Never mind. Okay, good. 104. Who has 104?
That's mine.
Okay, Nada.
So I got for the rhythm, it's normal rhythm.
Okay.
For the heart rate, it's around 75 BPM.
Mm-hmm.
For the axes, I got a normal axis because leads 1 and AVF are positive.
Mm-hmm.
The PR interval looks about normal. And
This is normal?
there's missing P waves in V1.
No. It's not missing P wave. It's not missing. Let's look at, for example, here.
Okay.
I think the PR is not normal.
Mm.
It's more than 0.2. You have to count in millimeters. I think it's more than 1.2.
Okay.
So that can be a first degree AV block. Okay.
Yeah. Mm-hmm.
Go on.
And the QRS interval is narrow.
Okay.
So we don't have an intraventricular like conduction.
Okay, good.
For the ST segment elevations,
pathological Q wave.
I don't see a pathological Q waves.
Good, go on.
I see an ST segment elevation in leads 2, 3, and AVF.
Very good.
And ST depressions in leads 1 and AVF.
Good. Very good.
So because I see an ST segment elevation in 2, 3, and AVF, I would say this is an acute inferior wall STEMI.
No, it's not acute because there is no pathological Q wave, only ST elevation. So that's an hyperacute inferior MI. Yes, and?
And we already mentioned the first degree AV block.
Yes, and? What about this ST depression in V1, V2, V3?
I'm not too sure.
Anybody has any idea about inferior MI plus an ST depression in V1, V2, V3? Mirror image of what? Inferior.
Anteroseptalis?
No. It's not an ST elevation. It's not an ST. ST elevation would be an anteroceptor. But this ST depression, it should be on the opposite wall.
Posterior?
What? Posterior. Yeah, be louder, please. Posterior. Especially when we do have an inferior, very frequently comes together with posterior. Because the same coronary supplies these two areas. And both is, if you close let's say, a bigger part of this right circumflex artery, yeah, the both can be seen. So here we do have a hyperacute infero-posterior myocardial MI. Yes, that's it. Okay. Good. 105. Wow, that's a great. 105.
Hello, it's me.
Okay, good.
So I put the rhythm, it's a regular rhythm.
Okay.
The heart rate is about 72 BPM.
Okay.
The axis, it's normal axis because in 1 and AVF it's positive and in 2 it's the highest. So it's around plus 60 degrees.
Good, very good.
The shape of the P wave are normal.
Okay.
For the PR interval, I see it's normal.
I don't think so.
Okay.
I don't think so. I don't think so.
So it's a bit wider. So we have a...
No. PR is shorter.
Shorter?
Right behind of the P, the QRS starting. See, can you see it?
Yeah, I see it.
So the PR is short and the QRS is wide. What does it mean?
We have an hypertrophy. No, not hypertrophy. No, sorry. It's wide, so yes, we have a problem for the conduction. We have a
faster conduction. We do have a faster conduction. What does it mean when we do have a faster conduction? Huh? Better conduction. That's good.
I don't remember.
Somebody? How do we call those syndromes when we do have a short PR?
Pre-excitation syndrome.
Yes, and there are, at least we learned 2 types of it, such as when we do have a wide QRS and starting with the delta wave, that is called WPW syndrome, Wolff-Parkinson-White syndrome, yes. And there are 2 types. Looking at V1 is negative or positive. Negative is a B type, positive A type. When we do have a negativity, meaning that can bundle located on the right side. If you do a positive, located on the left side. So that's a B type WPW syndrome, yes?
Okay, B type.
Okay.
So it's located in the right. Yeah, right.
Yeah, because going away from V1, this is why it's on the right side. Okay. Pathological Q wave. Can you see pathological Q wave?
No.
Yes.
V1, yeah, but
and V2.
Yeah, because it's inverted, but I think it's with the Wolff-Parkinson syndrome.
Yes, very good, very good, very good. Exactly. So not every pathological Q wave means MI. See? Because in WPW syndrome, we could have pathological Q wave. We could have in V1, V2. We could have in V2, V3, for example, can be. Or we could have a pathological Q wave in left bundle branch block. We can have QS complex in V1, V2, V3. Yes, that's a left bundle branch block. Itself can cause it. Now, in a case of left bundle branch block, however, because it's difficult to diagnose an anterior MI, unless you do have ST elevation in V6, V5, it's okay. That case, you can say that that's a left bundle branch block plus NMI. But if a patient never had left bundle branch block, and together with the typical pain of MI, they do have left bundle branch block, you have to assume that the patient has MI, okay? Now, and another thing that I want to say, look at here, this ST segment. Look at here, the ST segment. Depressed.
Yeah, depressed.
Okay. This kind of ST segment depression, that's secondary due to WPW syndrome. So if you do have, for example, abnormal conduction, such as, for example, well, is here, I cannot see nicer, but in left bundle branch block, right bundle branch block, or WPW syndrome, that is called secondary STT changes. This is not due to ischemia. We can explain why the ST segment is altered. This is why it's called secondary. If we cannot explain, that's a primary or that's an ischemic changes, okay?
Okay.
All right, so that's only WPW syndrome and B type. Good. What about this sign? What do you think? What is this?
I thought it was just the end of the... I don't know, really.
Somebody? That's a calibration sign, 1 millivolt calibration sign. Okay, this square signal is a calibration sign. It should be 10 millimeters. Okay.
Okay.
Good.
Thank you.
106, 106. Who has 106?
I have this one. It looks rhythmic. The heart rate is around 60 beats per minute. The PR looks normal and it looks like a sinus rhythm.
Okay.
the QRS are narrow
Mm-hmm.
and the axis is normal.
Okay.
I see an ST elevation in lead 2, 3, and IVF.
QRS, pathological Q wave first.
I don't see any pathological Q waves.
It's good for you. It's not good for the patient. Yes, there are 2, 3 AVF. Yes.
And I think there is an inverted T wave in lead 1.
ST segment. Okay, step by step. Don't fly. Let's walk only. Okay. So first of all, we saw this Q wave in 2, 3 AVF. Another lead. Well, nothing. Maybe in V6 you do see, but I don't think that is wide or bigger than 1/4 of the R wave. So assuming that could be normal. Okay. Let's look at now the ST segment. As you see here, ST segment is elevated in the same leads when we were talking about the Q wave. Yes? So
Yes.
that meaning we do have a
MI.
2, 3. What is the location?
Inferior.
Inferior. Immediately you should look at the chest leads in V1, V2, V3. Can you see any ST depression? No, you don't. So there is no posterior MI. That's it. Okay. So what we have an acute inferior MI. That's it. Okay. And nothing else. Good. All right. Go on. Next one. 107. Who had 107? Nobody. 108. Nobody. 109. Nobody. Who has the next one? Come on. Are you here? Hello, guys.
Yeah, we are here.
Okay, who has ECGs?
I do, but I have 115.
115. So
yes, please.
Before nobody.
I have 111. 111.
111. So 1010. Nobody has 110. Nobody. 111. Okay. It's your turn.
Yes. Okay. So the given graph, it is rhythmic. The heartbeats is 60 ppm.
Okay.
We can see their sinus P waves are positive. I think PR is normal. QRS seems narrow. So the axis is normal too.
Very good.
And I can see AVF, it is positive, which is about 60. And also we can see pathological Q waves in V1, V2.
Okay.
And ST elevation in V2. So I think it is septal acute myocardial infarction.
Very good. Very good. Very good. You can say that it's a septal myocardial. Okay. Good. Very good. Okay. Good. Okay. 112. Nobody? 113. Wow, that's a nice ECG. Nobody?
Yes.
Okay, Mickey, come on.
Firstly, like our distance is constant, so it's rhythmic. And then heart rate is like 50 BPM, so it's 50. Yeah, it's bradycardia.
Yeah, it's 1, 2, 3, 4, 5, a little bit less than, more than 5. Okay, so it's 50, 55. Okay, bradycardic.
And then like heart axis, when I check the lead one, it shows the positivity. And then when I check the AVF, it also shows the positivity. So it is located within normal axis. And then, yeah, like I can see the, like when I compare the one to AVR, like AVL, I think like AVL shows the like negativity, like shows negativity. So when I sum up all the read, it is located at 160 or 190, like hard axis.
No.
Oh, okay.
No, AVL is negative, meaning that is less than 60. And if you do compare, let's see the 1, 2, 3, you do see that 1 is bigger than 2. So this is why it's closer to 0. Okay, so I would say this is around AVR, lead number 3 is negative, so it's between 30 and 0. Okay, 30 and 0.
Okay. And then
now E wave.
I don't think, oh, yeah, P wave is like peer interval is longer than the normal.
Very good, very good. I would assume that the PR is okay. So we do have P wave and looks like it's a sinus P wave, but the PR is longer than normal. Okay, go on.
So like it means there is the like block between the like conduction, like atrium and the ventricle.
Okay, very good.
And then I can see the notched QRS.
Before we go to the notched QRS, is the QRS wide or not?
Wider.
Good. What does it mean?
There is, yeah, like there is like abnormal conduction within the interventricular space.
Okay, so which one? V1 and V6.
Left bundle branch block.
Left bundle branch block. Very good, because you do see the wide R wave, notched R wave on the left side. Very good. So we do have a left bundle branch block. Okay, go on.
And then like when I check the lead 2, 3 AVF, I can see the ST elevation. So
okay,
there is inferior MI.
Okay.
So when I check the like 1, 2, 3, 4, 5, 6, there is also like elevation.
Okay.
Elevation. So like anterior lateral.
No, that's not. Okay, we do see Q wave here, V1, V2, V3, but this is can be due to left bundle branch block, okay? Because left bundle branch block. Okay, now ST elevation can be the sign, okay? V5, V6, okay, there's a lateral leads, or it can be a sign of the posterior wall as well. And if you do see here ST depression, you can see here a little bit, okay? And that's an infero-posterior myocardial MI. So we do have a left bundle branch block, first degree of AV block. This is called together. If we do,
yeah, inferior posterior, like inferior posterior hyperacute.
Okay, plus you do have a
left bundle branch block. So like I would like to ask one question. So like for V1, V2, briefly shows the ST depletion.
If here only I do see the ST depression in V2, I don't see other lead. So I'm not sure that there's a posterior or not, but that's an inferior for sure. And the inferior sometimes give you an ST elevation on V6, V5 as well. So it's possible that maybe the posterior wall is not affected because we have to have ST depression at least 2 consecutive lead, but we don't have. So I would say that's a inferior hyperacute MI. We do have a left bundle branch block and a first degree AV block. How do we call together when we do have a first degree AV block and the left bundle branch block? That's a trifascicular block because the anterior, posterior plus the first degree AV block.
Could you repeat it again?
We have 3 fascicles is blocked. Anterior fascicles, posterior fascicles, and AV block. Trifascicular block. Okay.
I have a
good.
question.
Now tell me, what is your question, Sarah?
You said it's a left branch block, a
yes.
block, because
yes.
of B1, B2, and B3 has inverted QRS?
No. Van der Waals block, because we do have a supraventricular rhythm, sinus rhythm, and the QRS is wide. This means we do have an intraventricular conduction abnormality. We should look at V1 and V6. Whenever you do see the wide R complex, notched R, the block is there. So we do have on the left side, this is why Mickey diagnosed the left Van der Waals block. That's it. If you do have a left Van der Waals block, it's meaning that anterior and posterior fascicles already blocked. And together with the first degree AV block, this is the trifascicular block. Go back to the previous class when we discussed the trifascicular, bifascicular blocks. Okay?
Okay, thank you.
Sorry, so this is like trifascicular block and the AV block with inferior MI. Hyper.
Yes. Yes. Oh, yes.
Thank you so much.
Okay, good. Okay, 114. Anybody?
That's mine.
Okay, let's see. Mao?
Yeah, it's rhythmic and heart rate is around 65 beats per minute.
Good.
And we can see P waves. And PR interval looks normal. And QRS looks normal. And the axis is lead1 is positive and AVF is positive, so it's within normal range. And lead1 has the highest amplitude, so it's around 30 degrees. And there is no pathological Q wave. And we can see ST elevation in lead 2, 3, and AVF. So it indicates inferior localization of myocardial infarct.
Hyperacute myocardial.
Yeah.
See? Okay, and there is nothing in the posterior wall, and you see, fine. You do see ST depression in lead AVL and lead number 1. That's due to the mirror image of the inferior wall. Okay? Good.
Okay.
115, not 115.
Yeah, I have that.
Okay.
Okay, so we have the BPM being around 100. It's first of all, it's rhythmic. BPM around 100, and we can see a sinus rhythm which seems normal. And the main, and then lead 1 and AVF are positive, so it's in the normal axis. But lead 2 seems more positive over here, so I would say around maybe 30. And the main issue over here is in the V's, so we can see a wider QRS from V1, especially V1 to V5. We can also notice, I think, a Q negative. Q, if it's normally negative, but it's a bit deeper over here. And what was the last thing? Yeah, so I thought that because it's from V1 to V5, then it would also be an anterolateral STEMI.
H1. Yes, it's it. Yes.
Yes, and then V1 is more positive than V6. So can we also say it to be a right BBB?
Yes, it's a right Van der Waals block. That's fine. That's fine. Okay. An additional one. You said that the QRS is wider in V1, V2, V3. No, it's wide everywhere, except you don't see where the QRS is starting. See, here, the S wave is very wide. Okay. So the QRS is narrow, but the S wave is wider one. This is why it's wide, but the S is slurred in V on the left side. So this is another proof of a right Van der Waals block. Good, very good. Okay,
thank you.
And by the way, guys, this ECG was solved before. Who could recognize this?
I think it was 103.
Yeah, 103. Yes, yes. See? Good. Somebody recognized it. Very good. Very good. Because usually if I give the same kind of ECG to you, you won't recognize again. Okay. Let's see. 116.
Yes, it's mine.
Okay. Let's see.
So first, heartbeat is rhythmic. And adult heart rate is 60 BPM, so it's normal.
Okay, good.
And regarding the axis, lead 1 is positive, AVF is negative, and lead 2 is positive, so adult it's left deviation.
Okay.
And when we look at PER interval, it looks normal.
Okay.
And QRS is narrow.
Okay.
And yeah, and when I look at V1 to V6, I see there's ST elevation and negative T wave.
Pathological Q wave first.
Pathological Q wave.
V1, V2, V4 for sure, and V3 you do see an initial R, but that's smaller than it should be, so the R regression can be. So I would say that pathological Q wave can be seen here from V1 to V4. Normally, we do not see any Q wave here. And ST segment elevation that you mentioned. So Q, ST elevation, again, V1 to V4, that meaning that we do have a anterior acute MI.
Okay.
Okay, good. All right, 107, 117. Anybody has this? I think, what else? Nobody has more? Let's check it. I'm going to check my list, but maybe there are no more. Yeah, 119, 119. Anybody has this?
Yes, I have it.
But you didn't say anything that who has more. Okay. All right. Now let's see. That's a weird ECG. Come on.
Okay, and it looks arrhythmic.
Yes, that's good. This is arrhythmic. Okay, go on. Heart rate?
And heart rate is around 75 in average.
I think it's less. It's, well, it's okay. It's about 100. Yes, about 75. So normal. Okay, go on.
And the axis.
Yes.
The lead 1 is positive and AVF is negative.
Okay.
So it's left deviation.
Okay, and 2 is negative. See, 2 is negative. Okay, because these beats are different one. See, these beats are not normal. What kind of beats are these?
It's
here as well.
It's premature ventricular.
Yes, and multifocal, because if you look at the lead number 2, there are several types. Okay, so that's QRS is different from this QRS. Okay, so that's a multifocal. Okay, so we do have a multifocal ventricular premature beat formation, and we do have an extreme left deviation due to, because well, this is again premature beat. I'm sorry. No, it's okay. You said it's a very good because 2 is positive. So that's only left deviation. Very good, because that's a ventricular beat as well. So these are couplets. Okay, these are couplets. These couplets, ventricular premature beats. Okay, good. Okay, go on. Whenever you do see the P wave, it's right somewhere here. See? We do see P wave, but very far from the QRS complex. Okay, so that's a first degree AV block. Whenever we do have a conduction, that's a first degree AV block, okay? Now, so we are not looking at the premature bits. We have to look at the normal bits, normal originated bits. And now we should see the Q, let's see the Q wave or ST segment. Look at in V2 again. See?
Yeah, there are pathological
Q wave and ST segment elevation as well. Okay. Mm-hmm. So that could indicate that's again, that's an anterior acute MI. So you can say that's an anterior acute MI with couplets, ventricular multifocal couplets, and that's it. And you can look at whether this kind of premature bit is overcompensated or not. Okay, so what we have to do, look at the distance. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 2 R's is 9. Here we have, how many is we have? It's right here, but something has happened in this area. See, this area, it's something weird happening here. It's another premature bit. I think that's another premature bit right here, because it's not a continuation of this whole thing. So, and I don't know what is a normal RR interval. Maybe this is a normal RR interval. Let's see, 1, 2, 3, 4, 4.5. So that means that's a compensated ventricular premature bit. And that, I believe, that's a premature bit, a supraventricular premature bit. If you assume that this is a P wave, it can be a atria premature bit. So this patient has a very severe ischemic changes. The ischemic change is manifested as a ventricle and atria premature bit formation, plus the typical sign of an acute MI. So this is what will happen if somebody has an MI, and an MI can alter the conduction system as well, and the impulse formation centers as well. So this is why when the patient has an MI, that's ECG is very weird one. Okay, I think that was the last one, yes? Okay, guys.